Hello, my name is Mikhail Khalilov. I am from the Scalable Parallel Computing Lab in ETH Zurich, and I'm extremely happy to present you our work on the efficient hardware resource management for the SmartNICs. This work is a collaboration between the ETH Computer Science and Electrical Engineering departments and Sapienza University of Rome. In this short introduction, I will discuss the importance of SmartNIC acceleration in modern data centers with respect to our work. A trend realized in the community is the increasing scaling gap between the speed of CPU and data center link bandwidth. The side effect of this observation is that with each new generation of NICs, it gets harder for the general purpose CPUs to sustain processing of packets at the line rate. A promising solution for this problem is the SmartNIC offloading approach. SmartNICs extend NIC programming capabilities such as RDMA to enable offloading of user-defined packet processing kernels, and these kernels are executed on cores collocated with the NIC DMA engine. Over the last 5 years, the community demonstrated how to leverage SmartNIC offloading to accelerate various data center applications such as consensus protocol, processing small RPCs, or reduced acceleration, and many others. SmartNIC extends the NIC pipeline with the processing cores, and we will call these cores packet processing units or shortly PUs. PUs are complemented with a memory subsystem which can constitute caches and NIC DRAM memory. And to leverage offloading, host application instantiates the application state and kernels in the NIC memory. After the initialization, NIC can receive packets from the network, and DMA engine forwards the packets into the PU memory. After that, the NIC processing engine can start kernel execution and process the packet. During the processing, user kernel can introduce various kinds of data movement. For example, it can generate packets towards the NIC egress, such as protocol acknowledgements or sequence of packets with IO read payload. After the packet processing is finished, the kernel can also notify the host site about the completion. For example, it can increment a counter of processed packets in the memory region mapped to the host site program. There are two types of SmartNICs offloading exist, and people distinguish between a so-called on-path and off-path offloading. The key difference between these offloading types is the placement and architecture of processing engine. But there is also a hybrid hardware such as BlueField-free that features both of them. But in this talk, for the clarity, let's keep this distinguishment between on-path and off-path offloading because it's important for the context of our work. On-path cores such as DPA directly interface NIC DMA engine. And the idea behind the on-path processing is to enable the workloads that exhibit high degree of data movement and packet parallelism, such as RPCs processing or MEL collectives. The on-path processing substrate constitutes tens to hundreds energy-efficient processing cores tailored for low IPC data movement. And these cores are typically programmed with a custom low-level C API. The off-path offloading, on the other hand, features a general-purpose systems on chips running Linux. And off-path cores are more suitable for the single-threaded branch-rich code that found in network virtualization functions and security offloading. Off-path approaches resemble host-side CPU architecture and exposes the same set of standard OS APIs, such as packet processing with RDMA and DPDK. In this talk, we will focus on the on-path offloading as it cannot leverage standard approaches for software data plane resource management. We expect that on-path acceleration will soon become generally available in virtualized data centers. In this context, goal of our work is to go further from the single application acceleration and to understand how the compute and I/O resources of SmartNIC can be efficiently shared between multiple applications. To answer this research question, we used an open source on-path SmartNIC, since The existing commercially available solutions, such as Bluefield DPA, are closed source. In our work, we used PSPin, an open-source SmartNIC developed in ETH Zurich. It features energy-efficient on-path acceleration that is based on the silicon-proven RISC-V cores organized in clusters. It is designed as a hardware IP block for integration with data center NIC data plane, similarly to the Bluefield DPA. PSPin SDK also includes a cycle-accurate simulation toolchain that we used for our experiments. Let's see now how well out-of-the-box PSPin schedulers can handle scenarios when two tenants share compute and I/O resources. For the compute scenario, we simulated two tenants with the same packet size. The victim tenant has a compute cost per packet which is twice smaller when compared to congester. Here we show an evolution of the processing cluster occupation with the time. And the congester flow starts after the victim flow occupies a whole cluster in the beginning. We see that the congester quickly occupies more than half of the cluster, which is unfair to the victim flow. The unfairness stems from the round-robin scheduling policy of PSP. And while we can leverage round-robin to efficiently distribute packets across PUs within a single application, the policy is unfair in multi-tenant scenario when tenants have different compute cost per packet. The second problem is when the NIC DMA engine is shared between I/O-intensive applications with different request sizes. Here we show how the kernel completion time of the victim flow with 64-byte I/O request can be affected by the congester with larger I/O size. Depending on the type of I/O operation, we notice 10 to 35 times slowdown for the victim tenant. The root of cause for this problem is the design of the PSPin DMA engine. The engine implements FIFO policy to serve DMA requests from the compute clusters, and FIFO processing results in the head-of-line blocking problem for small DMA requests that are blocked behind the large ones in the DMA queues. So now we've seen the need for the resource management in the SmartNIC data path. But why not to use existing management solutions developed over the past 15 years for the software data planes like DPDK? The problem is that at the fully utilized NIC link, the per packet processing budget is extremely tight. For example, in this plot, we show how the per packet cycle budget at 1 GHz and 400 gigabit per second increases with a packet size. We compare it to the kernel execution time of various compute and I/O intensive workloads such as packet payload reduction and I/O RPCs. In this setup, we notice that to keep the link busy, we need to spend less than 1 microsecond per packet. This deadline becomes even tighter as the packet gets smaller. While the many-core on-path offloading will be an ideal choice for this kind of workloads because we can hide the low IPC processing, the single-core compute power of on-path SmartNIC will not be sufficient to run something like centralized software scheduler, and we will not be able to meet such small deadlines. To address this challenge, we introduce OSMOSIS. OSMOSIS is a hardware operating system for the SmartNICs, and it constitutes a set of lightweight hardware schedulers to support fair share of resources between SmartNIC tenants. OSMOSIS scheduling policy is controlled through the simple software API to enforce sharing resources across tenants, such as compute utilization, DMA bandwidth, and memory allocation size. OSMOSIS architecture constitutes several components. During the offloading initialization, the data center administrator sets the SLO policy. She specifies the tenant priorities for the compute, I/O, and egress resources, and the policy is associated with a SmartNIC virtual function. The tenant can create an offloading execution context within the virtual function. And the tenant execution context is represented in the hardware with a lightweight abstraction that we call flow management queue, or shortly FMQ. FMQ stores packet flow descriptors, scheduling state, and other offloading metadata such as pointers to the tenant kernel. Part of the FMQ metadata is the matching rule that can be used to match packets to this FMQ. For example, we can use matching rule to match packets based on the IP address tuple. Once the packets are matched to the FMQs, the OSMOSIS compute scheduler assigns them to the processing units. In addition to that, two I/O schedulers arbitrate DMA and network I/O requests from the kernels running on PUs. We use a hybrid compute scheduling policy to enable fair resource sharing with a minimal hardware footprint. The key idea behind this hybrid scheduling is to maintain the information about the current FMQ compute utilization. To explain the mechanics of our scheduler, let's now consider the following example with 3 FMQs and 64 idle processing units. Let's assume that after some time, the PUs in our system became saturated with the work. And let's see now how our scheduler will choose the next FMQ after one of the PUs will complete packet processing. In this example, PU2 just finished the processing of the packet belonging to the FMQ1. And it sends a feedback signal to the scheduler to update the FMQ1 state. Now, the scheduler can pick the FMQ for the processing. To maintain the fair share of PUs between FMQs, the scheduler will pick the packet from the FMQ with the smallest current utilization. The utilization is also scaled by the FMQ priority. And in our example, the FMQ2 with the lowest PU usage is the FMQ2. So its packet will be processed next. By evaluating the Jane's fairness index on the compute resources utilization, we see that OSMOSIS scheduler achieves perfect fairness of sharing PUs between tenants. The second component of OSMOSIS is an I/O resource management. Our current prototype supports software and hardware fragmentation methods to enable round-robin scheduling of active DMA requests. Software method performs fragmentation of large requests into the smaller ones in the DMA runtime middleware. This approach doesn't require any additional hardware logic, but increases latency of the transactions. And hardware method, on the other hand, introduces additional hardware state for outstanding requests, but keeps per request latency minimal. On the right side, we evaluate scenario when the I/O towards the NIC egress path is initiated from the victim and congester kernels at the same time. We compare 64 and 512 byte fragmentation versus no fragmentation at all as a baseline. As the congester request size grows along the horizontal axis, in the below subplot, we notice the lower impact on the kernel completion time, thanks to the request fragmentation. Yet, this improvement comes with the reduced throughput for the congester flow. This overhead stems from the added AXI protocol overheads to process a larger amount of smaller transactions. And in the paper, we actually discuss the possible solutions for this, such as extensions to the AXI protocol. Last, I would like to present the key results of OSMOSIS system evaluation. We evaluate OSMOSIS from 2 angles. First, we assess the added hardware footprint by synthesizing the OSMOSIS hardware blocks. And second, we evaluate OSMOSIS in the cycle-accurate simulation on realistic packet traces at 400 gigabits per second. On the left side, we show the comparison of the synthesized round-robin and borrowed virtual time schedulers. And on the right side, the gate footprint of maintaining the state from multiple concurrent DMA requests. While the OSMOSIS scheduler logic has 7 times higher footprint when compared to the round-robin, the overall gate consumption of the scheduler remains within the 1% of the total SmartNIC IP block. For the DMA scheduler, the gate footprint doubles with the number of supported concurrent DMA streams, and support of 32 concurrent streams will take below 3% of the total SmartNIC chip logic. Overall gate consumption of OSMOSIS schedulers is below 5% of the total area of the SmartNIC, which is quite small. In this experiment, we compare OSMOSIS performance to the baseline PSP network interface card. We use statically generated packet trace with 4 tenants, and we have 2 tenants with the small read and write requests and 2 tenants with the large requests. Similarly to the synthetic scenarios, we notice that OSMOSIS able to provide a fair resource utilization along the system runtime. And as a bonus, OSMOSIS policy also leads to the up to 60% reductions in the tenant flow completion times. In the conclusion of my talk, I would like to highlight key takeaways of OSMOSIS. We identified that supporting multi-tenancy in the 400 gigabits per second on-path SmartNICs will require hardware resource management. To address this, we introduced OSMOSIS, a hardware resource operating system that enforces fairness of resource sharing between SmartNIC tenants. We discussed key components behind the OSMOSIS management, such as compute and I/O schedulers, and we demonstrated that they can achieve fair SmartNIC resource sharing with a minimal hardware footprint. You can check out the OSMOSIS source code on our public GitLab, and thank you for your attention.